Section 4.5, Integration by Substitution. Up to this point, we have only been able to integrate functions that were already separated out into terms. In math, we like to use substitution to break down a more complicated problem to a more manageable one. The technique of substitution is going to help us integrate functions that are in the form of a composite function. These composite functions can be in the form of products, quotients, and even powers. The role of substitution in integration is comparable to the use of the chain rule in differentiation. So let's go back and look at the chain rule for derivatives. Given that y is equal to f of u and u is going to be g of x, find the derivative of f of g of x. Now, in order for us to find the derivative of this composite function, we need to use the chain rule. The chain rule states that the derivative will be the derivative of f of g of x times the derivative of g. The way we've stated this in class is we take the derivative of the outside function, rewrite the inside function, and then multiply by the derivative of what's inside. Now, in theory, when we have the derivative of this composite function, we should be able to integrate it to get back to the original function that we had to begin with. So, if we integrate that composite function of f prime of g of x times g prime of x dx, we know we should go back to the composite function of f of g of x plus our constant of integration. Now, I'm going to go in here and make this look just a little bit simpler by using my substitution that u is equal to g of x. So I'm going to restate this and say the integral of f prime, and instead of g of x, I'm going to substitute the letter u, and then instead of g prime of x dx, I'm going to say that that is the derivative of u. And that is equal to f of, once again, g of x is going to have substitution of u plus the constant of integration. This formula right here is what we are going to use to do the integration of composite functions. Let's try a couple examples. In this first example, the integral of 2x times the quantity of x squared plus 1 to the fourth power dx, what we want to do to begin with is we want to look for the composite function. And more important, we want to find the inside function for the composite function. So the inside of the function is going to be the quantity of x squared plus 1. This quantity of x squared plus 1 has been plugged into this fourth power polynomial. So what I'm going to do is I am going to let u equal the inside of the composite. So u is equal to x squared plus 1. Now, according to our formula right here, we need not only the function evaluated at u, but we also need to know the derivative of u. So if u is equal to x squared plus 1, the derivative of u is du, the derivative of x squared is 2x, the derivative of 1 is 0, and this is multiplied by dx. Think back to your differentials. So now when I come over here to my integral, I can rearrange my terms, and I can take x squared plus 1 to the fourth power, and I can rearrange this 2x and dx and set them next to each other, and say that this is going to be 2x times dx. Now, the reason that I went ahead and rewrote them is because we can see right here, this piece is going to be u raised to the fourth power, and this piece right here is equivalent to du. So what I can do is I can substitute my u and my du into my integral in order to make a more manageable, easier to integrate function. Now, once I have this in the form right here, this is simply using our power rule to integrate. So, to integrate this, we're going to increase the exponent by 1, that brings it up to an exponent of 5, divide by the new exponent, so that gives us a coefficient of 1/5, and then we have our constant of integration. Now, you do need to do one more thing, because this answer is in terms of the variable u. U was a substitution variable that we chose in order to make the problem easier and more manageable. However, the final answer should always be back in terms of the original variable, which in this case is x. So what I'm going to do is I'm going to come back up here to my u being equal to x squared plus 1, and I'm going to substitute that in for u. So we'll have 1/5 times the quantity of x squared plus 1 to the 5th, and then plus our constant of integration. And I do not expect you to FOIL that out. Let's try another one. The integral of 3x squared times the square root of x cubed plus 1 dx. Now, once again, you must look for the inside of the composite function. That should always be your first step. So when I look at this, I see x cubed plus 1 as the inside of a square root function. So that is what I'm going to let my u represent. So u is going to be x cubed plus 1. Now, once again, in our formula, we need not only the composite function, but we need the derivative of the inside. So if the inside function u is x cubed plus 1, the derivative of u is going to be du. The derivative of x cubed will be 3x squared. The derivative of 1 is 0, and then times dx. So once again, if I come over here and I rearrange my terms, I'm going to move this 3x squared, and I'm going to combine it with the dx that we have at the end. So we will have the square root of x cubed plus 1 times 3x squared dx. Now, looking at this, I should be able to find these two pieces in my integral. So this first piece right here is going to be u to the 1/2 power, the square root. And then this piece right here, 3x squared, that's exactly what we need, and replace it with du. So using the substitution variable of u, we can rewrite this more complicated integral into something that's easier to work with. Once we get it into this more manageable integral, once again, we are going to use the power rule. So the power rule says we're going to add 1 to the exponent. That brings this exponent up to 3/2. Divide by the new exponent. That gives me a coefficient of 2/3. And then plus our constant of integration. The last thing we need to do is to go back to the original variable. Right now, my substitution variable of u is in my solution. I need to go back to my original variable of x. So I am going to go back and substitute x cubed plus 1 to the 3/2 in for my u. And there's our answer. Let's make things a little bit more complicated. So now that we've gotten the hang of finding what the u should be, that's going to be our inside of the composite function. So u is x cubed plus 5. And we also know that we need the derivative of u. So the derivative of u is going to be 3x squared dx. Now this time when I rearrange my terms, we've got a little bit of a problem. So we'll have x cubed plus 5 raised to the 6th power. I'm going to rearrange my x squared. I'm going to move it over here next to the dx. So we'll have x squared dx. But this time we are missing a piece. If you notice up here in the du, we're supposed to have 3x squared dx, and we don't have the 3. Now, that's a problem. However, it's easy to fix. What I know is that we are allowed to multiply anything in math by 1, and it will not change the value of our expression or of our function or of our value. So what I'm going to do is I'm going to strategically multiply by 1, but I'm going to introduce the number 3. So I am going to multiply my integral by 3/3. Now the reason that I did that is because once again I can rearrange my terms and I can place that 3 over with my du pieces. So what we have now is the integral of 1/3 times x cubed plus 5 to the 6th power times 3x squared dx. So even though we were missing the coefficient that we needed for du, we were able to put one in by multiplying top and bottom by the same number. So now when we do our substitution, we're going to have 1/3 x cubed plus 5, that's u, so this will be u to the 6th, and 3x squared dx, that's our du. So we were able to rewrite our integral in terms of a more manageable format. Once again, to integrate this, I'm going to add 1 to the exponent, so that gives me u to the 7th, divided by that new exponent gives me a coefficient of 1/7, and then plus our constant of integration. So we now have 1/21 u to the 7th plus c. And then the last thing we need to do is to go back to the original variable. Once again, my original variable of u is equal to x cubed plus 5. So we're going to substitute that back in. So 1/21 times the quantity of x cubed plus 5 raised to the 7th plus c. Now, once again, we are allowed to multiply by the value of 1, and we can strategically choose how we want to represent 1. As long as it's a constant, you are allowed to do that. However, if you're off by a variable, then you're going to have to try another strategy. This substitution and multiplying by 1 is only going to work if you're off by a constant. Let's try another one. Last one, the integral of 5x cubed over 1 plus x to the 4th raised to the 2nd. Now on this one, I can see that the composite function has the inside piece of 1 plus x to the 4th. So I'm going to let my u substitution be 1 plus x to the 4th. That means my du, the derivative of 1 is 0, the derivative of x to the 4th is 4x cubed dx. So let's look at what we have here. We have the integral of, and I'm going to move my terms around a little bit. I know that I need the x cubed, so I'm going to slide that over. We have 5 over the quantity of 1 plus x to the 4th, and then I'm going to put that x cubed dx together. Now, the problem is that I need a 4. I don't have a coefficient of 4, I have a coefficient of 5. Now, it's really not quite as complicated as it sounds at first. Trying to figure out what we should multiply to make my 5 turn into a 4 is actually not terribly complicated, but it does take a little bit more work. My suggestion is to come in here, since we need a 4, and let's multiply top and bottom by 4, and then move the 4 over with the rest of our du. So now what we're looking at is 5 over 4 times the 1 plus x to the 4th quantity squared, and then 4 times x cubed dx. So our 5 is still sitting here. The 4 we've moved over to join the rest of the pieces of the du, and the 4 is still sitting here. Now, once again, this is a constant that we can move across the integral, so we can factor that out and say 5/4 times the integral of, this is going to be 1 over u squared times du. Now, the best way for us to handle a variable that's down in the denominator is to rewrite it with a negative exponent. So we're going to say that this is u to the negative 2nd du, and then use our power rule from there. So 5/4 I'm going to rewrite. We're going to increase the exponent by 1. That gives us u to the negative 1st. Divide by that new exponent, and then we have plus c, our constant of integration. Cleaning this up, we have 5/4, negative 5/4 over u plus c. And then the last thing we're going to do is we're going to plug in the 1 plus x to the 4th to substitute the u back out. So negative 5 over 4 times 1 plus x to the 4th plus c. So if you're missing a constant that you need for the du, it's very easy to put that in there. You just need to remember to balance the top and the bottom. If you multiply by 4, you also have to divide by 4 to keep it balanced. And if you have extra constants that are kind of in the way, they're not what you need, you can always just kind of move around them, leave them where they are, and put in the values that you need and work from there. So now you're ready to try these on your own. Good luck.